So number of ways of distributing m different balls to n persons so that each person can receive any number of balls. So this you can consider as two sets. A contains the m elements x1, x2, x3 and so on xm, and B contains the n elements y1, y2, y3 and so on yn. So here where number of ways of distributing m balls to n persons. That means first ball can be given to any of the n persons, so n ways. Second ball also can be given to any of the n persons. That means n into n into n and so on m times, which is same as n to the power of m. So in terms of functions, this corresponds to number of functions. That is number of functions from set A containing m elements to a set B containing n elements is n to the power of m. Next, number of ways of distributing m different balls to n persons where m less than or equal to n, so that each person can receive at most one ball. In the previous case, each person can receive any number of balls, whereas here each person can receive at most one ball. That means either no ball or only one ball. So first ball x1 can be given to any of the n persons, that is n ways. Second ball can be given to remaining persons only, that is n minus 1 ways. Third ball n minus 2 and so on m balls, it is n minus m plus 1. This you can convert into factorial notation, n factorial upon n minus m factorial. In terms of permutations, it is npm. So in terms of functions, it is number of one-to-one functions from set A containing m elements to a set B containing n elements. So number of ways of distributing m identical balls to n persons so that each person can receive at most one ball. Now, so the first person can receive any of the ball, that is n ways. Second person n minus 1, third n minus 2 and so on. Because the balls are identical and each person has the same number of balls. So in the denominator it will come as m factorial, which is same as n factorial upon m factorial into n minus m factorial, which is ncm. Next, number of ways of distributing m identical balls to n persons so that each person receive at least one ball, means it can be one or more. Is now that means we are having m balls which are in the plane. Now we have to distribute this m balls to n persons such that each person can receive at least one ball. That means I have to break this arrangement of m balls to n persons. That means I can keep some gaps in between only, not to the extreme positions. That means these gaps or breaks are possible in between. So in between there are m minus 1 possibilities are there, and the gaps will be n minus 1, so that the parts will become n. So it will be m minus 1 c n minus 1. And this statement is also same as number of positive integral solutions of the equation x1 plus x2 plus x3 and so on xn equal to m, where xi greater than or equal to 1. Because we are saying positive integral solution means it must be starting from 1 onwards only, which is also same as m minus 1 c n minus 1. Number of ways of distributing m identical balls to n persons so that each person can receive any number of balls, means it can be 0 or it can be more, which is same as another way of saying the same statement is number of non-negative integral solutions of the equation x1 plus x2 plus x3 and so on xn equal to m. That is non-negative means 0 can be included, that is xi greater than or equal to 0 for all I equal to 1 to n. Now that means m balls are there, so arranged in a row, and this balls we have to distribute to n persons. That means we need to make it n minus 1 gaps. That gaps can be used to the left of the first ball or to the right of the ball also. That means I can take some sticks which are identical and place it in between the balls. That means it will be like arrangement of letters, some are identical. That is m balls are identical and sticks are also identical, n minus 1 gaps. That means arrangement of this. So total is m plus n minus 1 factorial upon how many are repeated? That is n minus 1 factorial into m factorial. Number of ways of distributing m different balls to n persons so that each person can receive at least one ball where m greater than or equal to n. Now, that is set A contains m elements and set B contains n elements. So here this entire statement will be same as the onto function. That is, this corresponds to number of onto functions from set A containing m elements to a set B containing n elements, which is n to the power of m minus nc1 n minus 1 to the power of m plus nc2 n minus 2 to the power of m and so on, plus minus 1 to the power of n minus 1 nc n minus 1 1 to the power of m. Now, this you can derive the formula using inclusive and exclusive principle. So if you have two sets, n of a1 union a2, you can write as n of a1 plus n of a2 minus n of a1 intersection a2. This you can understand from the Venn diagram also. Now, if you have three sets, n of a1 union a2 union a3, n of a1 plus n of a2 plus n of a3 minus two sets at a time, that is n of a1 intersection a2 minus n of a1 intersection a3 minus n of a2 intersection a3. Next, three sets at a time, that is plus n of a1 intersection a2 intersection a3. This also can be derived from the previous formula, or else from the Venn diagram also you can identify this. Next, this can be extended further to any number of sets. So n of a1 union a2 union and so on an equal to sigma I equal to 1 to n of ai. This is like n of a1 plus n of a2 plus and so on n of an. Then this contains n terms. Next, after that, minus two sets at a time, that is sigma n of ai intersection aj I less than j and I and j from 1 to n. That means 1 1 you cannot get, 1 2 1 3 and so on 1 n. After that 2 1 will not be there, 2 2 will not be there, 2 3 2 4 and so on. That means here when I expand the sigma, it contains nc2 terms because you are taking 2 at a time from n elements, so it contains nc2 terms. Next, here nc3 and so on, ncn means only one term. So this is called inclusive exclusive principle. So the derivation of number of onto functions formula. Now, so number of onto functions is set A contains m elements and set B contains n elements, and such that each element in the codomain should have at least one pre-image. That in terms of balls, number of ways of distributing m different balls to n persons so that each person receive at least one ball where m greater than or equal to n. Let us denote some set notations as ai. I am denoting as ith person receive no ball. That means a1 means first person receive no ball, a2 means second person receive no ball. Now, what will be the number of elements of a1? That is n of a1 means first person is not receiving any ball. When first person is not receiving any ball means y1 is not getting any ball. That means it is a way possibilities of distributing m different balls to n minus 1 persons. That is, first ball can be given to any of the n minus 1, second ball also to the any of n minus 1. That means n of a1 will become n minus 1 to the power of m. Now, not only n of a1, n of a2 also will be the same. Meaning of n of a2 means second person receive no ball. So second person is not receiving any of the balls. That means again you are distributing m balls to n minus 1 persons only. That is, whether it is n of a1 or n of a2 or n of an, it is always same as n minus 1 to the power of m. Now ai complement. That means complement of this means ith person receive at least one ball. So when ai denotes receive no ball, so ai complement denotes ith person receive at least one ball. Now if I take two sets at a time, intersection, ai intersection aj means ith person and jth person receive no ball. Now if I consider n of a1 intersection a2 means first person and second person are not receiving any of the ball. That means m balls you are distributing to remaining n minus 2 persons. So first ball can be taken any of the n minus 2, second ball also any of n minus 2. That means it will be n minus 2 to the power of m. Not only first and second, even first and third, first and fourth, also it will be the same. Now, as per the statement or definition of onto functions, in terms of the set notation, number of onto functions can be written as n of a1 complement intersection a2 complement intersection a3 complement and so on intersection an complement. The meaning of a1 complement is eighth person receive at least one ball. That means first person receive at least one ball. Not only first person, second person also, third person also. That's why we have taken as the intersection. Now using the De Morgan's property, this we can write as n of a1 union, a2 union, and so on union, an whole complement. Now using the complement definition, that is n of a complement is n of mu minus n of a, where mu is the universal set. That means this we can write as n of mu minus n of a1 union, a2 union, and so on union an. Now n of mu as it is minus. This is an inclusive exclusive principal formula which we discussed before. That is sigma equal to 1 to n of ai minus sigma I less than j n of a intersection aj plus and so on. Now n of mu means number of functions from set A to set B. Set A contains m elements, set B contains n elements, which is n to the power of m minus. Here n of a1 will be n minus 1 to the power of m. N of a2 is also n minus 1 to the power of m. And this sigma contains n terms. One at a time we are taking. That's why it is nc1 n minus 1 to the power of m. Minus of minus plus. Now here the number of terms are nc2. That is nc2 n minus 2 to the power of m and so on. Now this term n of a1 intersection a2 intersection an value will be 0. Why? Because a1 intersection a2 intersection an means first person is not receiving any ball, second person is not receiving any ball. That means all the persons are not receiving any of the balls. That means this term will be 0. That means before this term will be minus 1 to the power of n minus 2 sigma of n of a intersection aj and so on will be there. So that how many terms will be there is nc n minus 1 terms will be there. So minus 1 to the power of n minus 1 nc n minus 1 1 to the power of m. So another concept is derangement. Let a1, a2 and so on an be n distinct objects such that their positions are fixed in a row. Now if we rearrange the a1 to an in such a way that no object occupy its original position, such an arrangement is called a derangement. So you are having n objects arranged in a row whose positions are fixed. After that, we are interchanging the objects in such a way that no object occupies its original position. So mathematically, you can relate this to a bijective function of a1 to an such that f of ai is not equal to ai for all I equal to 1 to n. So under this condition, it will be a bijective function, means it will be one-to-one function as well as onto function. That is, domain is a1 to an, codomain is also a1 to an, and we are not assigning a1 to a1, but we are assigning a1 to any of this, but distinct element will have distinct images, as well as codomain is same as a range. That's why it is one-to-one as well as onto. So now formula for the dearrangement is, if n distinct objects are arranged in a row, then the number of ways in which they can be rearranged so that none of them occupy its original position, denoted by d of n. That is derangement of n distinct objects. Now, so this formula is again can be derived using the inclusive exclusive principle. That is what we discussed before, number of onto functions, exactly same manner you can proceed. So here n of a1 means first person is not receiving any of the ball. That means n balls you are giving to remaining n minus 1 persons only. That is, first ball you are giving to any of the n minus 1, but second ball to the n minus 2 persons only. Why? Because here position is fixed. That means only one ball only can be received. That means n of a1 will become n minus 1 factorial, and the same manner n of a1 intersection a2. That is, first person and second person are not receiving any of the ball. Then all these balls to the n minus 2 person means it is n minus 2 factorial. So when you apply the formula and simplify, then you can find the d of n is n factor into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial and so on minus 1 to the power of n upon n factorial.